So this video is about the discovery of the atom and the development of atomic theory. Alright, so what is an atom anyway? Well, an atom is basically the smallest particle of an element that retains the properties of the element. They're like the building blocks of the Legos of the world. Think of it like this. So copper conducts electricity. It's why we use copper wires in computers. A lump of copper will conduct electricity. If you split the lump up, it still conducts electricity. Split that lump up some more, and it still conducts electricity. But once you try to split it too small, though, it'll stop conducting electricity. And almost all the other properties also change. So basically, we decide to draw the line of the atom at the point where further breakdowns fundamentally change the properties. And this is kind of true. There's actually some cool philosophy that goes into what is an atom and what's not. So this is a simplification, and you could argue with it. But it's simple enough for this class. And that's when you reach the atom, when an additional cut fundamentally changes the properties. So the model of the atom we use in this class is kind of like this. You have neutrons and protons that hang out in the nucleus of the atom, the middle right here. And then you have electrons that sort of circle around the outside. Now this is not technically what an atom looks like, but it's the model that we're going to use for this particular PowerPoint. But how do we get this picture? How do we know that there were neutrons and protons in the middle and electrons on the outside? So let's start at the very beginning, the four elements. Way back in the day, ancient civilizations, specifically Greece, sort of believed that the world was made of basic elements that combined in specific ways to give us the universe. These are the Avatar Airbender elements. You have fire, earth, air, and water. You also have some basic qualities, like they thought hotness, wetness, coldness, and dryness were also fundamental things, and so the combination of air, fire, water, earth, and hot, dry, wet, and cold made up the entire universe. You could explain it all. But this was not the case. So you don't really need to remember it, but it's good to have a picture of where we started, so that you can know how much progress you made. So the first person to come up with the concept of an atom was Democritus, an ancient Greek philosopher. He thought that if you cut up an object enough times, you would reach some little indestructible chunk that you couldn't break down anymore. And he decided to call this chunk this thing, which is a Greek word that I can't pronounce. But it's kind of like atomos, which is the English version of that, I guess. And it means indivisible or uncuttable in the language he used. So this word atomos, uncuttable, is where we get the word atom today. It comes from Democritus, ancient Greece. And this is a Eurocentric class. So that's why I'm teaching you that Democritus was the first guy to come up with the theory of the atom, but he wasn't. There were other atomic theories in other cultures before this, like, for example, in India specifically. There was a Hindu sage who theorized about the existence of fundamental atoms. In other cultures, people figured this out or came up with the idea before Democritus, but we act like Democritus came up with the idea because the modern scientific tradition is mainly from Europe, and Europe really likes Greece and Rome. That's where we say that our intellectual grandfathers are from. So that's why I'm teaching you that Democritus is the father of the atom. But he's not really. This is basically how the conversation went. There was a rock. Democritus said, "What happens if I broke the rock?" And somebody else said, "Well, it would probably break into little pieces." And Democritus said, "Okay, but what happens if I break those pieces?" And he said it'd probably break into even smaller parts, right? But what happens if I broke those smaller parts? I was like, Democritus, where is this going to end? It's like, what if I broke those? And at that point, people stopped paying attention and decided that air, earth, fire, and water were preferable to Democritus's ravings. And he was not happy that nobody believed what he believed, but hey, we're learning about him now, so I guess he was right in the end. So that was Democritus, right? But it was not a very scientific theory. He just decided that there was the smallest thing. So Dalton came up with the first real scientific theory of the atom. So Democritus didn't have any evidence, just a thought experiment. And then in 1803, a scientist named John Dalton came up with actual evidence that should be named. And I don't know if it was actually in 1803. This is just when this picture was taken. It was around 1803, though. So he also came up with a set of postulates, which is sort of like a scientific word for rules or statements about atoms and their properties. And these are Dalton's postulates, the things that he thought about atoms. All matter. Everything is made of atoms. Atoms of the same element are exactly the same and differ from atoms of other elements. So like oxygen is like every other oxygen atom, but is very different than other carbon atoms. He thought that atoms could not be cut up, created or destroyed, like they're indivisible, indestructible, they don't have parts. He thought that atoms of different elements combine in whole number ratios to make compounds. Now this sounds kind of complicated, but basically what it means is that you never have an oxygen combining with half of a hydrogen. You can only have one atom. You can't have a decimal number of atoms. So whole number ratios, not fractional ratios. And then in chemical reactions, atoms are combined, separated, and rearranged. So he had 3 pieces of evidence to support his conclusions. The first one was conservation of mass. And basically every single reaction you ever do, the mass of what you start with is the same as the mass that you end with. And this is not obvious, because you think that if you burn a log, that the log is heavy and the ashes are light. But really, if you take all of the log and the air that reacts with it, put it on a scale, well, in outer space, put it on a scale, on one side, and then on the other side you have the burned ashes and the gas that you make at the end, they are exactly the same mass. And this makes sense, and it supports his theory, because if atoms are only rearranged, then you have the same number at the beginning and the end, right? 4 yellows, 8 blues at the beginning, and you end up with 4 yellows and 8 blues, just combined in a different way. They have the same mass, so this is the same as this, mass-wise. So the law of conservation of mass. Mass is never created or destroyed. And this is not technically right. We discovered in a very sophisticated way it's a little bit wrong, but it's right enough for you to learn it now. It's basically true. Think of it like a law. Next, the law of definite proportions. So this means that whenever you find a certain chemical, you will always find it composed of the same ratio of elements. So like this is copper hydrogen carbonate. Maybe you've seen it before. People like to show pictures of it because it's a really pretty rock. It's also used to color the tops of buildings, and it's used to pigment some other things. And no matter where you find it, here or here or here, it will always have the same ratio. It'll always be about 60% copper, about 35% oxygen, about 5% carbon, and about 1% hydrogen, because this is the chemical formula. Everywhere it is, it's made of the same molecules, and each molecule has the same ratio. So every single time you see a chemical, it has the same proportion of elements. So this also supports this atomic theory, because molecules bound together like this would give you the same proportion everywhere. And here it is. In simpler terms, a single compound will always be composed of the same elements in the same ratio. His last piece of evidence, the law of multiple proportions. So if you start with the same elements, but you combine them in different ratios, you get different chemicals. This makes sense if the properties of a substance are determined by the way the atoms are rearranged, not just the kinds of atoms you have. And this is an example. So this is laughing gas. 2 nitrogens, 1 oxygen. They use it to knock you out when you have dental surgery. This is nitric oxide. It's a health supplement. It supports a strong cardiovascular system. Basically, it opens up your veins and lets the blood run through. And this is nitrogen dioxide. It's a pollutant that some studies say cause asthma in children, and it hurts your lungs. So, knocks you out, opens up your veins, hurts your lungs. These are very different properties. But the same elements, nitrogen and oxygen, are in all of them. So you can have the same elements in different proportions, and you have different properties. To put that another way, different compounds with different properties can be produced using the exact same elements if you use different proportions. So Dalton's atomic theory was not correct. Not all atoms of the same element are exactly the same, and atoms are not indestructible. They have parts, protons, neutrons, and electrons. So these are called isotopes, same elements but different, like you have radioactive versions of carbon and non-radioactive ones. And then also, this one is not really true, because in outer space you have really cool things like neutron stars, and we're not going to get into that right now. Just pretend like this is true, because for the most part on Earth it is true. These are the 2 that are generally considered to be wrong. So next, after Dalton, they discovered that the atom had parts. Back here, Dalton thought that the atoms didn't have parts, but we figured out that they did. J.J. Thompson discovered it with a cathode ray tube experiment, and then he also made a plum pudding model. Basically, this is a cathode ray tube. It's a hollow tube with no air, 2 pieces of metal, and a detector. You run through some electricity, and you create a beam, a cathode ray beam. That's what they called it. So he discovered that this beam was made of a bunch of little particles, because the detector picked up patterns like this. The beam hit the wall, And then you got a bunch of little hits. Not one constant big hit. A bunch of little flickers. Which doesn't make sense if this is just one really big laser beam. So the detector pattern let him know that the beam was made of a bunch of particles. And when the particle hit the wall, it made a hit. So you had a bunch of different little hits. Hit, 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 hit. Also, the particle had shadows, so it had mass. It wasn't just light. Because light doesn't make shadows. So that's how he discovered that the beam was made of particles. And then he also discovered that the particles were negatively charged. Because when you shoot the cathode ray beam and you put it through an electrical field, it's attracted to the positive and repelled by the negative. So you can think of this kind of like magnets. You know magnets, you have north poles and south poles. And the opposite poles, they attract each other. And the similar poles, they repel each other. Electricity works basically the same way. So we shot a beam, and the beam was repelled by the negative and attracted to the positive. So this made sense because the beam was made of particles that were negative, right? Because if they were negative, they would be attracted to the opposite and repelled by the same. So that's how we figured out that these particles were negative. But then he did one more thing. You notice he has the same piece of metal here every time. So maybe electrons are not in all atoms. Maybe they're just in some kinds of metal atoms. So he tested out different materials. And every material he tried produced the same kind of electrons, the same kind of beam with the same properties. So this indicated to him that every single kind of atom had these electrons in it, not just some. So his experiment, J.J. Thompson, proved that electrons exist. They're negatively charged. But scientists already knew that normal matter does not have a total electric charge. So what's up with that? I mean, everything has electrons. Electrons are negative. So why isn't everything negative? And this is how it works. You remember from algebra, positive one and negative one, you add them together and you make 0? Similar things happen with charges. If you have an equal amount of positive and negative charge, they cancel each other out and become neutral. So J.J. Thompson knew the electron was negative, so the atom had to have other positive things in it to cancel it out. And this is the model he came up with. A big positive dough with little negative chunks in it. The positive and negative cancel out, so it's net neutral, but it's broken up in pieces like this. He called it the plum pudding model because plum pudding is a kind of British dessert where fruit is baked into dough. It's like a fruit cake. So imagine that you have a big spherical fruit cake with little pieces of fruit inside. You can also think of it like the chocolate chip cookie model because these are kind of like chocolate chips in a big cookie dough. So that was J.J. Thompson. Now we go on to Ernest Rutherford. So this is not what the atom looks like. It wasn't the picture that we had at the very beginning. Rutherford gets us to the picture we had at the beginning, where you have the electrons orbiting the nucleus kind of like planets. And that model's not exactly right, but it's better than the plum pudding model, right? So Rutherford set up an experiment. He had a gun that shot alpha particles at a gold foil. Basically, he expected that every time he shot a particle, it would go straight through. Because, I mean, imagine you're shooting a machine gun at a ball of plum pudding, right? Every bullet would go straight through this dough because the dough is not very dense. Go straight through. But this is not what happened. Sometimes the particles went through, and sometimes the particles bounced off, which is bizarre. So the particle went through sometimes, and then they bounced off sometimes. And this is his train of thought. Basically, if the plum pudding model was correct, the particle would go straight through because it's not very dense. Now, the fact that the alpha particles bounced means that they hit something very dense. Imagine that you shoot a bunch of bullets at plum pudding, they go straight through, right? So imagine they hit something very dense in the middle. And also, it has to be a positive core because these alpha particles are positive. So if the core was negative, then the particle would come and stick together like a magnet. Only if they're positive will they repel. Anyway, so he shot alpha particles, and if the particle hit the nucleus, it bounced. If it did not hit the nucleus, it went straight through. Like imagine that you have a plum pudding, but with a steel core in the middle. Basically, most of the time you shoot at it, the bullet goes through. And the bullet goes through. But if you by chance hit this core, it'll ricochet, bounce back. So he discovered the nucleus. He discovered that the nucleus was made of positively charged particles, which we now call protons, and he discovered that it was very dense, that the rest of the atom was pretty much empty space. That's it. Summary of the people and concepts. In the very beginning, we didn't believe in atoms. Then Democritus came up with the concept of an atom, with his word atomos, which means uncuttable. Nobody believed him, though. Then Dalton came up with the first scientific theory of the atom. He had 5 postulates and 3 basic pieces of evidence supporting his theory. Thompson discovered the electron, which is the first part of the atom to be known, by using a cathode ray tube to discover that the particles have negative charge, because he put the electric field and they deflected. He came up with an incorrect plum pudding model of what the atom looked like, and then Rutherford picked up where Thompson left off and discovered protons in the nucleus by the gold foil experiment, where he shot alpha particles and watched them bounce off the dense, positively charged mass in the center of the atom. That's it. The development of the atomic theory. That's not it. There's a lot more that goes with that, but that's what you need to know. Hopefully that was helpful.